Today class will discuss about the gas power cycles, and last video we have seen the Otto cycle, diesel cycle and Carnot cycle. Okay, this is the new topic. There is a gas power cycle where we use a gas as a working medium in order to convert the heat energy into mechanical work. Okay, so the gas power cycle is also called as a Brayton cycle, yeah, and also it is also called as a Joule cycle. Okay, let us first know what is the working principle of this entire gas power cycle. The main important components or parts of this gas power cycle is we have a centrifugal compressor, combustion chamber, turbine as well as heat exchanger. First, what we will do here is a simple process, as we will take the air from the atmosphere and it enters into the compressor where it compresses, the air compresses and it passes to a combustion chamber, where in a combustion chamber burning of the fuel or heating of the fuel takes place. After that it enters to a turbine. In a turbine some amount of mechanical work will be done and the hot gases will expand in the turbine and it will move on to heat exchanger. Heat exchanger where the hot gases leave the heat to the atmosphere and again the cycle repeats. This is the basic principle of the gas turbine. Let us know the what is, and it is a thermodynamic cycle, and here will let us know about what is PV and TS diagram. Same here, PV diagram, pressure volume diagram as well as the temperature entropy diagram. As I told, first 1 to 2 is the center, that is the compressor, compression, isentropic compression will be done. Here some amount of compressor work will be done, no heat supplied or rejected takes place here. And from 2 to 3 is the constant pressure process where the heat addition takes place exactly here at isobaric process, and 3 to 4 is the expansion or some mechanical work will be done in the turbine, that is 3 to 4 is expansion process. Whereas 4 to 1 is the heat rejection takes place, that is at a constant pressure process. So as you should know that what is the importance of your compressor and turbine will do some amount of work here, whereas the heat rejection as heat addition takes place at the combustion chamber and heat rejection takes place here. Okay, so first as I told that first we have 1 to 2 is the isentropic expansion compression, 2 to 3 is a constant pressure heat addition process, whereas 3 to 4 is isentropic expansion, 4 to 1 is constant pressure heat rejection. First, as I told that the heat addition takes place in the process 2 to 3. So I'll take heat addition takes place at isobaric process. That process I'll take it as 2 to 3 process. So that I can take Q1 is equal to mCp T3 minus T2. How you can take this T3 minus T2? You can see in this TS diagram, highest temperature is 3, 2. So I'll take as T3 minus T2. And heat rejection takes place at the isobaric process. As I told, the heat addition in case of this gas power cycle takes place at a constant pressure, that is isobaric process. So I'll take Q2 is equal to mCp T4 minus T1. Same, the temperature at 4 is highest to this one, so minus 1. So that I'll take it as T4 minus T1. Next, as I told, the heat addition and heat rejection takes place at the constant pressure process, that is isobaric process. Now I should take the what is a compressor work as well as a turbine work. So compressor work takes place from the process 1 to 2. So I'll take it as WC is equal to Cp into T2 minus T1. And turbine work takes place from the process 3 to 4. So that I'll take it as Cp T3 minus T4. Okay. So now we know what is efficiency. Efficiency is given by the formula work done divided by heat supply. Work done divided by heat supply. So what I will do is total work I will take W divided by Q1. So as we know that what is the total work is equals to turbine work minus compressor work. Now I will substitute what is the turbine work is Cp into T2 minus T1, Cp into T2 minus T1, again minus what is the work done in compressor, what is the turbine work is Cp into T3 minus T4, T3 minus T4 minus compressor work is taken as minus Cp into T2 minus T1. Okay, so now W is equal to Cp. I'll take Cp common here. If I take Cp common here, T3 minus T4 minus into plus is minus T2, minus into minus is plus T1. I can write like this because I am taking the W common here. W is equal to Cp. Sorry, W I am taking here. Cp I am taking common. Cp into T3 minus T4 minus into plus is minus T2, minus into minus is plus T1. Next, what I will do here is same. I will rewrite this one. W is equal to Cp into Cp. I will take common. So I will write it as T3 minus T2. This I will take it as Cp minus T2 minus Cp into that is T3 minus T2 T3 minus T2. If I take minus common, I can write like this. That is T4 minus T1. So this is the total work done. How is that? Because here if I take minus common here, so minus into plus is minus T4, minus into minus is plus. So if we rewrite the above equation, rearranging the above equation, I am rearranging above equation. So if I rearranging the above equation, W is equal to Cp into T3 minus T2 minus T4 divided minus T1. Now I will take efficiency equation. Efficiency is equals to total work done divided by heat supplied. So now efficiency is equals total work done is Cp into T3 minus T2 minus T4 minus T1. This is the work done divided by heat supplied is heat supplied. I told to take MCP. Heat supply takes place from the process 3 to 2. So MCP T3 minus T2. Now what I will do here is I will take mass is equal to unit mass. M is equals to 1. Now see here, I will take efficiency, separate the terms. Cp T3 minus T2. If I take M as 1, now separate the denominator, that is Cp into T3 minus T2, minus, separate the terms, Cp into T4 minus T1, in denominator you will get Cp into T3 minus T2. Now what I will do, you can see here Cp T3 minus T2, Cp 3 minus T2 get cancels. So I will cancel, Cp get cancels. So efficiency is equals to 1 minus T4 minus T1 divided by T3 minus T2. So this is the first important formula you should keep in mind, that is efficiency is equals to 1 minus T4 minus T1 divided by T3 minus T2. Now what we should do, we should determine the different ratios here. So what I will do here is, listen carefully here. So 1 minus T4 minus T1. So here what I will do here is, I will take 1 efficiency is equals to, I will take in this formula, you take T1 common here T2 common. So now what I will do here is, efficiency is equal to 1 minus, if I take T1 common here, so I will take T1 common, so I will get T4 divided by T1, so that I should take LCM here, so I will get T4 by T1 minus, I will get 1, because I have taken the T1 common here. Similarly in the denominator I will take T2 common, T2, if I take T2 common, I will get T3 divided by T2 minus 1. This I will consider as equation number 5. This is I consider equation number 5, because here take T1 common in numerator, and T2 common in denominator. So that I am taking this one. So I will get efficiency is equal to 1 minus T1 into T4 minus T1. I am taking T1 common here. So I will get T4 by T1 minus 1, T2 divided by T3 minus T2 minus 1. This I will take. Now we should take the different process I should take here, that is from process 1 to 2. This is isentropic compression. So I should take the TP ratio here. So 1 to 2 is the process I should take, that I will take a TP ratio, that is T2 by T1 is equals to P2 by P1 to the power of gamma minus 1 by gamma. This is very, very important formula, that is T2 by T1 is equals to P2 by P1 to the power of gamma minus 1 by gamma, where P2 by P1 is taken as pressure ratio RP. I will take it as RP. So now T2 by T1 is equals to, so I can write this as RP to the power of, P2 by P1 is RP to the power of gamma minus 1 by gamma. So this I will take it as equation number 6. Similarly, if I take for the isentropic expansion, compression, I should take for the isentropic expansion. I have considered for process 1 to 2 as isentropic compression. Now I should take for the isentropic expansion. Now I will take here process expansion. Process is from 3 to 4. From process 3 to 4 I should take the TP ratio again, that is T3 by T4, similar same procedure, that is I'll take here T3 by T4 is equals to same I should take here T3 by T4 is equal to P3 by P4 to the power of gamma minus 1 by gamma. But from PV diagram, you can see here from PV diagram, we can write P3 is equal to P2 because it is a constant pressure process. Similarly, I can write P4 is equal to P1. Okay, so because it is a constant pressure, addition and rejection takes place. So I'll take P3 is equal to P2 and P4 is equal to P1. Now I'll take here from PV diagram, P3 can be written as P2, whereas P4 can be written as P1. Now I'll substitute here. So T3 by T4 is equals to P3 by P4 can be written as RP, that is P2 divided by P1 to the power of gamma minus 1 by gamma. Again this P2 by P1 can be written as RP. So T3 by T4 is equals to RP to the power of gamma minus 1 by gamma. This I'll take it as equation number 7. Now compare equation 6 and 7. Now compare equation 6 and 7. Now you can see that one of the side is same for both. You can see that one of the side is same for both. So you can see here RP to the power of gamma minus 1 by gamma. Here also RP to the power of gamma minus 1 minus gamma. So that from when one of the side is same, we can equate the other two sides. So I'll take this as T2 by T1 is equals to T3 by T4. Now see here, listen carefully. Now we have from in the equation 5 we have T4 by T1, here we have T2 by T1. So what I'll do, I'll cross multiply like this. So what happens here, T4 by T1 is equals to T3 by T2. So I can write, this is very important equation, that is T4 divided by T1 is equals to T3 divided by T2. This is equation number 8. Now what I'll do is from equation 8, so now in this equation, from equation 8, substitute T4 by T1 is equals to T3 by T2 in equation 5. Now I substitute T4 by T1 is equal to T3 by T2 in equation 5. Now what I'll get, efficiency is equals to 1 minus T1. In the place of T4 by T1, I will write it as T3 by T2 minus 1. T3 by T2 minus 1. Sorry, T3 by T2 minus 1 divided by, again what we have, T2. Here or do you write directly T3 divided by T2 minus 1. Here you can see that both the terms cancels here. Both the terms cancels. Remaining what we have, efficiency is equals to 1 minus T1 by T2. 1 minus T1 by T2. So we know that already. We know that T2 by T1 is equals to P2 by P1 to the power of gamma minus 1 by gamma. So where T2 by P1 is a pressure ratio, so I can write it as RP to the power of gamma minus 1 by gamma. Now substitute this in the above equation. So efficiency is equals to 1 minus, in the place of T1 by T2, in the place of T1 by T2 by T1 is RP to the power of gamma minus 1 by gamma. Whereas we can write T1 by T2 can be written as 1 by RP to the power of gamma minus 1 by gamma. So now substitute here. So final efficiency. So we will get the final efficiency equation. Efficiency is equals to 1 minus 1 divided by RP to the power of gamma minus 1 by gamma. This is the final efficiency of the Brayton cycle or a Joule cycle or a gas power cycle. Whereas RP is nothing but we can call it as the pressure ratio. It is given by the formula P2 by P1. Whereas gamma is nothing but we can call it as the adiabatic index. It is taken as the adiabatic index. Okay, so this is the final equation. This is the final equation of the Brayton cycle, or we can call it as Joule cycle. First, what I did, I have considered the total efficiencies taken by the total work done divided by heat supplied, and I have given the efficiency equation. After that, we have to take the isentropic expansion compression ratios and consider the PV diagram and take the isobaric process, and finally I have derived the efficiency of the Brayton cycle. Thank you.